from the University of Massachusetts at Amherst. She worked as a postdoctoral scholar at LIGO lab at Caltech, and also worked at the LIGO Livingston detector during the very first detection of gravitational waves in 2015 from a binary black hole merger. Jess has really had an incredible leadership role in the LIGO collaboration. She led the LIGO-Virgo publication outlining evidence that that first merger in 2015 was really an astrophysical signal and not noise. She's also been a key member of the writing team for the first detection paper of the merger of a binary neutron star in 2017. So she's worked with the LIGO instrumentation and data analysis group for more than a decade. She's a senior leader of the LIGO detector characterization group, and she's been really just a linchpin for building a LIGO collaboration and a really strong working group at UBC as well. Invested in detector development and characterization here in Canada. So she's been worked a lot on validation of candidates, and I think she'll talk to us about that today, and has also got a lot of insight into the upgrades and all of the effort being put into developing advanced LIGO, so all the engineering and other upgrades for continuing to kind of break open this really fabulous new area of astrophysics, which is giving us such cool new insights into the universe. So Jess, welcome. We're excited to have you here today, and take it away.
Thank you very much, and thank you for having me. So I am right now looking to see if I can figure out how to, so can everybody see my slides in presenter mode, or are they in audience
presenter mode?
Thank you for that warning. How about now? Did that work?
Yeah, that's better.
Beautiful.
Okay, fantastic. Thank you so much. And like Daryl said, so I work at the interface between the data analysis and the gravitational wave astrophysics and the LIGO detectors. So if you have any questions about any aspect of the experiment or the analysis, then please feel free to ask anytime, and I'll do my best to answer. So I always like to start with an overview. I see a lot of new faces here, and welcome to the seminar. So what's really interesting about gravitational waves from the perspective of astrophysics is that they're really weakly interacting. So they're generated by accelerating asymmetric matter. So we get this view of the dynamics of systems as opposed to electromagnetic radiation that generates light signals. And the fact that they're really weakly interacting makes them really difficult to detect, as we'll see. But it also means that we get this really crystal clear and sharp image of the dynamics of these systems. So gravitational waves will propagate without interference from dust or other matter. They'll travel for billions of light years, essentially unaffected, and give us that sharp view of cosmic collisions and distant explosions. So gravitational waves have already given us some really key new insights in fundamental physics and astrophysics. So we've already seen that gravitational waves can provide an independent measurement of the Hubble constant. So this comes from this direct measurement of the distance that gravitational waves gives us. And we'll learn a little bit more about that in a couple slides. We also, with gravitational waves, can gain this new insight into really highly compact matter, primarily from neutron stars. So either as they're spinning, if they have some deformity, some mountain or valley on them, and they're spinning, we can use gravitational waves to probe this equation of state of this highly dense matter, and also from the gravitational wave signatures of the tidal deformation as you have a neutron star that's merging with another compact object and being ripped apart. We can also use gravitational waves to do these novel tests of general relativity in a really strong field regime as you have two compact objects, particularly a heavy black hole, merging together. And what we're starting to see now, less than 5 years after the first detection, which won the Nobel Prize in 2017, you're seeing gravitational waves giving us this population, this census of stellar remnants across cosmic time that's going to allow us to infer the role of these dead stars in the evolution of the universe as we see it today. So let's start from gravitational waves themselves. So how do you make a gravitational wave? So what you're seeing on the left here, I hope you can see my mouse okay. So this is space-time strain. So what gravitational waves are is the stretching and squeezing of space-time. And this is the space-time strain amplitude. So this is how big the wave is. So you can see this time series. So this is strain amplitude over time. And how you generate a wave, so it's proportional to this really, really small number. So this is the gravitational constant g, a very, very big number in the denominator. So this is the speed of light to the 4th power, just so you can get a sense of how very tiny this amplitude number is. And then there are 2 important things to recognize here from this equation. So one is that this amplitude is directly proportional to this second time derivative. So what this is the acceleration of what we call the quadrupole moment. So this is essentially some asymmetric distribution of matter. And we'll see that 2 compact objects that are orbiting each other are going to generate quadrupole moments. And the other thing that I want you to notice about this equation is that this amplitude scales as 1 over the distance away. And we can build gravitational wave detectors that can measure directly the amplitude. So unlike a telescope, say, where you're measuring, your signal comes in flux, where you're essentially looking over the area of some detector, that's going to scale as 1 over r squared. Whereas we're going to be able to measure space-time strain as 1 over r, which allows us to sense very, very far out into space, where we're making these measurements of the mass of black holes and neutron stars. So one other thing that's important to notice, so this is strain as we measure it. So let's say we have a gravitational wave, it's been generated with the merger of 2 black holes, it's propagating at the speed of light through space-time. So what we're going to measure, how space-time appears to us as the stretching and squeezing, is this change in length over length. So this is depicted here. You get this kind of orthogonal stretching and squeezing. This actually comes in 2 polarizations that are rotated by 45 degrees. But what you can see here, if you can directly sense this relative stretching and squeezing, this is the time series that you'll read out. And again, this corresponds directly to this amplitude of the dynamics of the system, what generated the gravitational wave. So keep this in mind. This is what we're looking to measure. This is the data that we hope our detectors will produce. And it's this orthogonal stretching and squeezing that motivates us to build 2 orthogonal arms. So this is the basic layout for the LIGO and Virgo detectors. And what you see is this coherent laser light that enters the detector. It strikes this beam splitter so that 50% of it splits off in the y direction and 50% in the x direction. And this light is going to travel for the advanced LIGO detectors for 4 kilometers. So for those of you who may have learned about the Michelson-Morley interferometer, this probably looks pretty familiar to you. And essentially this is indeed basically a giant Michelson interferometer. And essentially what we're doing is we're looking at the differences in phase, the differences in the amount of time that it will take a wavefront of light to travel down each one of those 2 perpendicular arms. And we can actually read that out directly as this interference pattern as at our output port. So essentially, this is very similar to this Michelson-Morley experiment that you may be learning about now. So we have 3 of these detectors, these large-scale, kilometer-scale detectors that are in operation in this last observing run that ended just this past March. So they all have the same basic form that you're seeing there on the lower left. You have this coherent laser light entering the detector, traveling 2 arms that are on the scale of kilometers, and then we're measuring the difference in phase in the light that's traveling in those 2 arms. So we have 2 4-kilometer long detectors in the US. So these are the 2 advanced LIGO detectors. So one's quite close to where I am in Washington State, and that's LIGO Hanford. And then another is down in the swamp near New Orleans in Louisiana. That's LIGO Livingston. We also have the Virgo detector. So this is a 3-kilometer long detector in Italy. So all 3 of these detectors are running in this past observing run. All three of them were also used to detect gravitational waves from the very first detected merger of a binary neutron star. So in the future, we'll expand this network even further. So you see there in Japan, there's a detector called KAGRA. So this is a 3-kilometer underground cryogenic detector that should come online in the next observing run. And then you also see LIGO India. So this will be another 4-kilometer long detector with the same instrumentation as the advanced LIGO detectors. And that's being built right now and will hopefully be online in the middle of this decade. All right, so we have our detectors. So they sense space-time strain. Now, how do we detect signals with this data that we are acquiring from our network of detectors? So happily, we have this very powerful technique called matched filtering. So what allows us to use matched filtering is that general relativity predicts really precisely what the time frequency evolution of our signals will look like. So this is what you can see here on the right-hand side. So let's say you have 2 black holes. So general relativity predicts that they're going to inspiral each other and they're losing energy. They're radiating away energy in the form of gravitational waves, which is going to spin their orbit up closer and closer together until they merge. And then this final remnant, this larger black hole, is going to ring down, kind of like it was struck by a bell. So this gives us this form, this inspiral merger ring down form. And what's going to govern this time frequency evolution is the mass of these 2 objects and their spin. So that's what's going to dominate the shape. So in order to, let's say, tease out this different variety of signals that we expect our detectors to be sensitive to, we make what's called a template bank. So this is what you can see here on the left-hand side. So each one of those dots is a different version of this plot that's on the right. So they're slightly different or potentially very different. If they're much lower mass, that can be much, much longer than what you see there on the right. And we can also make our computational job a little bit less expensive if we put some realistic kinds of constraints on them. So for example, if they're low mass, so below about a couple solar masses or consistent with a neutron star, we can limit how much they're spinning to be consistent with neutron stars that are in binaries that will merge within a Hubble time in our own galaxy. So that actually lowers the number of waveforms in our template bank quite a bit. So we use GR, we predict the time frequency evolution of a whole bunch of signals that we expect to span the sensitive frequency range of our detectors. So the image you're seeing on the left, this is from 2016, where we had about a 500,000 or so, or on that order of templates. And now we have over 1 million templates that we're searching for, including heavier mass black holes, total mass black holes, than you see here on the left, and which will be important a little bit later on. Okay, so we have our template bank, and now what do we do with it? So you can see here on the right, so this is a time series of amplitudes. So let's say space-time strain over time. So we've got this noisy data here in blue, and then buried in this noise, we have some real astrophysical signal. So what we're going to do for each and every one of these dots that we have here in our template bank, we're going to calculate the signal-to-noise ratio, which is related to this cross-correlation. So essentially, we're taking the inner product between our data, so that's an S, and our templates. And so we've divided this up into the sine and cosine components. That has to do with the polarization that we mentioned a little bit earlier. But this is essentially the idea. So let's see what happens. So for each one of these templates, we're going to drag this along our data in time, and we're going to calculate this cross correlation, this inner product between the data and the templates. And even if it's not an exact match with the signal, we're going to see a spike. If it's a close match, if it has some strong overlap, we're going to see this spike in cross correlation or signal to noise ratio. And this is what we would call a trigger. So this is an event candidate that we have calculated using match filtering. So let's say we have a candidate with a pretty strong signal to noise ratio, and let's say it appears in all of our detectors. So this is a really important check that we expect gravitational waves to travel at the speed of light, so they should propagate through our detector network. So our next challenge is then to assess how significant is this candidate. So the question is, how likely is it that some random coincidence of noise events would have produced a candidate with some equivalent network signal to noise ratio. So this is just the quadrature sum of the SNR in each one of our detectors. So what we can do is we can compare, so the dashed line that you're seeing here, so this is the SNR of some particular candidate event. And what we do is we compare it directly to the distribution of our measured noise event rate. So we need to do this directly, sort of empirically, because LIGO and Virgo noise is non-stationary, non-Gaussian, it's almost impossible to model. So what we do is we actually use the data itself to generate this estimation of the rate of noise events. So in order to get this distribution, like you see on top in those two plots, we can do a technique called time slides. So this is what you're seeing here at the bottom. So I have, for each one of my 3 detectors, I have some set of triggers over time. So these are my candidate events, and I've noted glitches as X's and real signals that are stars. So in order to measure the chance rate of noise coincidences, what I do is I take each one of those streams of data and I slide it in time by some time that's greater than the travel time between the sites. So it's about 10 milliseconds or so. And so now anytime that I see a coincidence between triggers, that must necessarily be due to noise. And I can slide this data again and again and again until I have this distribution that's this measurement of what I expect my chance noise coincident rate to be. And now I can directly compare my candidate SNR to my noise event rates for some equivalent signal to noise ratio. So what you're seeing, the difference here between these two plots. So there are 2 ways that I can improve the significance of my event. So on the left, if I reduce the noise background, so if I push down the tail of my noise event distribution for an event that has some registered signal to noise ratio, so this is purely a function of the noise in the detector and the strength of the signal itself at the time of its arrival, I can increase the significance of that event if I reduce the background distribution of my noise. And the plot you're seeing there on the right, so let's say I have some given set distribution of noise events. So I can also increase my the significance of a given event, let's say for some signal with that's a certain distance away and a certain total mass. If I push down the average noise, then that will also increase the significance of my event. So there are 2 different ways of thinking about this, but essentially the idea is that you compare your signal to noise ratio as it's measured across your detector network to your expected rate of chance coincidences from noise. So let's say we've done this, and now we have a really significant candidate, and our next challenge is to infer what it is. So what were the 2 compact objects and how far away were they? So what we can do to give you kind of a cartoony idea of how this works is we compare our data in time and frequency, and we look for a match in phase, this time frequency evolution. And to first order, we can vary the total mass. So this is going to change the phase of our model, and we're going to line that up with the phase of our signal until we get a good match for the total mass of the system. And then again, remembering all the way back to our strain, our space-time strain generation, we can actually scale that directly to infer the distance. So this is this direct distance estimate. So let's see what this looks like. So we're evolving our model. We are changing the total mass until we have this good match in phase. And now we can scale directly to get this estimate of the amplitude. And then what I'm going to do is now, lastly, I apply the same bandpass filter as I did to my data. And now I have this very good fit and an estimate both of the total mass of the system and also the distance away. So this is a simulation that was produced for the very first detection. So this is 150914. But of course, in practice, it's not quite so straightforward. So we actually use a fully Bayesian parameter estimation framework. So what you're seeing here, so this is for the previous catalog of gravitational wave events that was produced by LIGO and Virgo. So each one of these traces is showing the posterior probability that each one of these sources is composed of a heavier mass. We call this M1, or the primary mass. of a certain value. And then on the y-axis there is the secondary mass, or the lighter mass. So what else you can see on this plot? So you'll see these different lines, these different dashed lines. So these represent different mass ratios. And the barrier between the gray and the posterior, so that's a mass ratio of 1. So all of our measurements so far are consistent with a mass ratio of 1 up to the third observing run. So we'll talk about some of our more exciting new observations in a bit from this past run. And something else that's worth noting is you see some of these, especially at lower masses, they tend to follow this funny kind of banana shape. So that's governed by this equation that you can see on the right. This is called the chirp mass. So this is a function of the product of the two masses, the two component masses that are merging, and their sum. So that's going to guide this chirp mass. We can resolve that really pretty well for lower mass systems. For higher mass systems, this is our uncertainty is a bit greater, and then you have the shape of the signal is more dominated by the total mass of the system. And we also have a method for detecting and characterizing signals that does not rely on match filtering or templates. So these are called our unmodeled burst searches, and the way that they work, so you can see 3 different time frequency planes here. So each one of those corresponds to a different detector in our network. And what we do is we whiten the data, we project it for each detector on this time frequency basis with wavelets. And then we look for coherent power that could have come from anywhere in the sky. And what we can do is essentially maximize the likelihood of the signal over all possible sky positions. And we can also use time sleds to estimate the rate of chance noise coincidences for the search as well. So this is a very, very powerful technique when you have the excess power in a signal is really well clustered together in time and frequency. So for high mass CBC mergers, so heavy black hole mergers, for example, we would expect the search to perform just as well as match filtering. And indeed, we'll see it does even a little bit better with some of our heavier sources. We would not, however, expect this to do well with a binary neutron star, something that has power stretched out for a very long time. And indeed, we can see this here. So this is a list of the 11 confident detections from this prior catalog, so GWTC1. So up top, you can see posteriors for mass. So for each of the 2 component masses, for the final mass, and also the total spin of the system. So those are up top. What I want to draw your attention to below, so I've highlighted 2 of these events here. So you can see their event name, which has the date baked into it, time of arrival, and then you have the results. So this is the significance or the false alarm rate for each of 3 different searches. So 2 of them are match filtering, so that's PyCBC and GST-LOL. And then we have our burst search, so that's coherent wave burst. And then also on the right, you can see the network SNR in each one of those. So I wanted to highlight 2 events here. So by far the loudest in SNR is actually the binary neutron star merger. So that's 170817 and this kind of salmon-y color at the bottom. You'll notice that that has no SNR in coherent wave burst. So it's by far the highest SNR signal detected with match filtering because it has hundreds and hundreds of cycles as it's in spiraling before it merges to integrate up that signal to noise ratio. However, if you look up at this magenta colored event, so this was prior to the 3rd observing run, the heaviest total mass source that we had detected. And now here we have an example of coherent wave burst having a really competitive signal to noise ratio, but you'll notice it has the most significant false alarm rates, the lowest false alarm rate. So I would also be remiss to not mention that there have been other claim detections from independent analyses from outside of LIGO and Virgo, which is really very exciting. So some you may have heard of from the Princeton group. So I've listed a table of these. So these are in addition to the confident detections by LIGO and Virgo. And then I plotted a couple spectrograms just below. Some of them do look really pretty convincing. And then there's also an additional catalog called 2OGC. So that's led by AEI Hanover and Syracuse group. And that's also linked here if you'd like to check that out. All right, and that brings me to some of our very first results from our latest observing run. So we've published 4 of them so far, 4 separate events from our latest run. So this run lasted from, I think we started April 1st, 2019, and it ran through most of March. We unfortunately had to end it a bit early due to the pandemic, but we have a lot of really great and exciting science. So the first result that was published was the second ever binary neutron star merger observation with gravitational waves. So this is 190425. So this is, if you're keeping track of the dates, also one of the first events that we observed in the last observing run. And on the left, what you're seeing, so this is a posterior likelihood or posterior probability that each one of the 2 component neutron stars has some mass. So for each one of these individually, their masses are consistent with neutron stars that we see in the galaxy, our own Milky Way. But if you look at the plot on the right, so this is probability density versus total mass of the system. So what's plotted in those green lines, so these are the measured masses, the total mass of binary neutron star systems in the galaxy. And then there's a histogram of those in gray and a distribution that kind of models that. And I also added a line in red that shows you where the total mass of 170817, the first binary neutron star merger with gravitational waves, would fall. But the posterior probability for the total mass of the system is not consistent with galactic binary neutron star systems, which is really very interesting. And if you notice in the top left corner of this particular plot, here again, you have this distinction between if you're restricting the spin of these systems. So we have made this choice to restrict the allowed spin of these systems to be consistent with what has been observed with electromagnetic radiation in terms of how much spin a neutron star would have if it's in a binary in our galaxy with another neutron star that will merge within a Hubble time. So now that we seem to have uncovered potentially a totally different extragalactic population, we may not be making that choice anymore in terms of future results. So here in blue, this is the posterior probability if you allow the spin of the neutron stars to vary all the way up to maximum spin. So the second results from the third observing run, so this is 190412, a binary black hole system of 8 and 30 solar masses. So this is really exciting because the higher mass ratio, so you remember all of our prior detections from the first 2 observing runs were consistent with a mass ratio of 1. But now here we have a mass ratio of almost 4. And it's this higher mass ratio, this bigger distinction between the 2 masses in this binary black hole system that allowed us for the very first time to observe these higher order modes. So if you remember all the way back to the beginning of the talk, we related space-time strain to the second time derivative of the quadrupole moment, and that is indeed the dominant factor. But you also get these higher mode contributions. And these are particularly visible, certainly not dominant, but detectable or starting to be detectable once you have a higher mass ratio. So to get a sense of what these higher order modes look like in terms of the geometry of the distribution of mass, I have some diagrams here. So this 2-2 mode, so this is the quadrupole moment that we usually quote, where you have these kind of symmetrically placed point sources that are orbiting each other like so. So for a higher order mode, so particularly for the 3-3 modes, we did detect some measurable SNR in this mode. You get this non-trivial distribution that still lies along the orbital plane of the system. But what we can see scientifically with higher order modes is that these allow us to better distinguish between some degenerate parameters. So for example, the plot on the left is showing you distance versus inclination angle. So we've talked about the amplitude of the signal. We can use the amplitude to infer the distance. However, there are other parameters that are describing the source relative to us, the observer on Earth, that could impact the amplitude. So one of those is the inclination angle. So it's the angle of the system as it orbits. So the amplitude is strongest if we're watching sort of face on this orbital evolution, and it's lowest if it's edge on. But the higher order modes have allowed us to really significantly distinguish between these two degenerate parameters. So you see here, so this is a posterior distribution. If you use just the dominant multipole, so that's in blue here, that's the 2-2 modes. And then there's a dashed line if you include the higher order multipoles, and then the posterior distribution that you see in orange. So this is if you're including both those and also precession. So this is a pretty exciting result that came out in the springtime. And shortly after that, we announced the third result. So this is 190814. So this picked up in the popular press as the mystery event. So this was a 23 solar mass black hole and a 2.6 solar mass compact object. So what you see here on the left, this plot, so this is again the primary, the heavier mass object, and the secondary mass on the y-axis, the posterior distribution for each of those. And you can see with a lot of different models, so most of them including both precession and higher order modes, so that's the PHM distinguisher that you're seeing there, they all constrain really pretty well that the heavier object is very safely a black hole, so about 23 solar masses. But the lighter object does fall between this observed mass gap between neutron stars and black holes. And there are a couple noteworthy points to make here. So this is comparable to the black hole remnant from 1708-17. So this is the first BNS merger observed with gravitational waves, and also the reports of a compact object by Thompson et al. In 2019. So also noteworthy, there were no electromagnetic counterparts observed for this signal, or tidal deformation effects observed within the gravitational waves. That's not too unexpected, even if it were a neutron star, just because of the distance, and also the high mass ratio works against us here, in that you'd expect the neutron star to get swallowed before it's torn apart too much. So the conclusion is that this is very likely a binary black hole system, but we can't definitively rule out other scenarios, like maybe a hypermassive neutron star that's supported by spin, or some kind of a exotic compact object. So that was reported pretty late in the spring. And that brings us to this latest result. So this is the fourth published results from our third observing run. So this is 1905-21. So this is the very first intermediate mass black hole detection, where we in gravitational waves define intermediate mass black hole as anything with a total mass above about 100 solar masses. So this system had an 85 and 66 solar mass black hole contributors. So what you're seeing here in terms of these plots, so on the left, so this is what the data looks like in the dominant detectors. So Hanford and Livingston had by far the strongest sensitivity. So I've shown them both here. Virgo was also online, and you can check out what their data looked like in the paper. So I've noted the archive number in the bottom. But what I'd like you to notice is that because the signal is so short, because there was such a small number of evolutions of this binary in-spiral, matched filtering did not pick up the signal very well. But the burst search did by a pretty large factor. So here the false alarm rates reported with coherent wave bursts. So that's 1 in about 5,000 years, which is a very significant event. And then for the best false alarm rate from a matched filter search, that was about 1 in 800 years from the matched filter search GST log. So this is not unexpected, but really quite remarkable in terms of a result with an unmodeled burst search. And then on the right, something else that's really noteworthy about this particular event. So this is again posterior probabilities for each one of these component masses. So you'll notice that the heavier mass, so this mass 1, so it's a very, very high probability that it falls in this pair instability supernova mass gap. So this mass gap exists when you have this electron-positron produced pair instability. So what can happen is you have some kind of a pulse where you have this temporary reduction in the radiation pressure of a star. So the star can pulse And this can generate potentially a runaway explosion. So you can either have the star shedding a lot of mass and also completely unbinding. Well, I see a question. Can we determine the individual masses? Ah, that's a great question. We can certainly constrain them very well. So I'll draw your attention to a few different curves here. So this is the plot on the left. So the light blue curve is the whitened data. So this is without any kind of a basis projection. The purple curve is this unmodeled waveform reconstruction algorithm called Bayes wave. So we can sort of agnostically to what we expect from general relativity, extract that waveform and then compare it to general relativity to do tests of general relativity, or to our models that include precession or higher order modes, and test and see where the data fits best. The orange curve is the matched filter, well, I shouldn't say that, the template-based Bayesian parameter estimation. And then the black curve you see is this coherent wave burst result.
So Jess, since you are answering Robert's question, there were some questions on the Slack.
Oh, okay. I am not tuned into that. Can you give me some highlights?
Yeah, for sure. So the first question was, what does the gray region on the plot in page 11 represent? It might be this mass plot. So could you answer that?
That's a great question. Ah, right. So this comes from our definition that mass 1 must be the heavier mass. This is kind of an arbitrary choice that we make in terms of numbering. But this is exactly what you'd expect to see. So the gray region is this boundary between mass 1 equals mass 2. Good question.
Okay, and then the next question was, are all the matched filters run through the data at the same time? Does the trigger typically only come up for one of them?
So they are run in as highly parallel of a form as we can make them. So particularly for online searches, a common technique is to break them up into chunks, so different ranges of masses, so that you do have sort of several different time series that are showing your triggers all at the same time. It gets a little bit tricky in terms of making sure that you're accounting for the right trials factor, but we try to get the information available as soon as we can.
Great. And the last question that's currently on Slack is, could you explain what the black hole remnants are?
Oh, do you have context for which ones in particular?
This sounds like a general question of like what is meant by black hole remnant.
Okay. So when I say the remnants, what I usually mean coming from the gravitational waves perspective is the final object that's formed after the merger. So either the merger of two neutron stars or the merger of two black holes. That's usually what I mean when I say the black hole remnant.
Okay, and that's it for what's currently on Slack.
Yeah, great questions. Thanks very much for asking them. Okay, well, I have a little bit more to say about this latest detection, things that I find really exciting about it. So I have up here on my subtitles, this is the first intermediate mass black hole detection, again, by the gravitational wave standards of being above 100 solar masses. So what you can see in the lower left here, so this is the posterior probability for the final mass of what I would call the remnant, so the final black hole post-merger. So this is definitively above 100 solar masses. So for us, it's unequivocally an intermediate mass black hole. You can also see the spin of the system. So it does accumulate some angular momentum from the orbit of the two black holes. So you would expect the final remnant black hole to be spinning quite significantly. So you might also notice that the peak of this posterior distribution and final mass is about 142 or so, which is not what I said in my abstract or what it says at the title of the paper, which is 150 solar masses. So what happened to those 8 solar masses? Well, they are radiated away in the form of gravitational waves. So in terms of energy luminosity, these are some of the absolute brightest events in the universe that will really briefly outshine every galaxy and star in the whole universe. It's quite a lot of energy. And something else that I think is exciting, so if you look at the bottom right-hand plot, so this is the tilt of the spin in angle. So the posteriors on the left kind of half circle, so this is showing you information about the spin of the heavier black hole, and the right-hand side half circle is showing you about the spin of the lighter black hole. So the angle is showing you what direction the spin of the black hole is pointing relative to the orbital angular momentum. So 0 degrees is aligned, and then 180 degrees is anti-aligned with the orbital angular momentum. But what you'll notice is that they both seem to be, there's a lot of probability that they have this significant tilt to them that's not aligned with their orbital angular momentum. So that combined with the very high mass of the system may indicate that this is a hierarchical merger, which means that one or more of these black holes, these initial black holes, is the product of a previous merger, and then they were captured and formed a binary dynamically somehow. So there are some pretty interesting theories for how this might have happened. Maybe this is in a disk of gas close to the center of a galaxy, or it could be some kind of a cluster of young stars that could potentially be favorable formation environments. But that's a very, very interesting, I think, result. Okay, well, this brings us to the end of our review of results and to one of the things I like most to talk about, which is the instruments. So you might be wondering to yourself, well, I had this really simple diagram of this nice Michelson-Morley interferometer. You've been telling me all these very interesting things that I can learn with gravitational waves, but how do we actually get that kind of precision with such a simple layout? And the answer, of course, is that we don't. So this is on the axis of reality here. So coming from our simple Michelson scheme all the way up to hundreds of thousands of moving parts that all have to fit together in harmony for us to be able to make these very, very precise measurements. So I'm going to take you on a quick tour. So we're going to zoom through, we're going to fly through one of the interferometers. So this is LIGO Hanford. And again, each one of those arms is 4 kilometers long. So 4 kilometer long Michelson interferometer. And what we're going to do is we're going to follow the path of the light from the laser source. So here you're seeing the vacuum. So I would come up to maybe about the middle or so of this tube here. But we're going to start from the laser source. So this is called the pre-stabilized laser, the PSL. So this is going to shoot first into this 3-optic cavity that you see in this kind of pink-purple color. So this is called the input mode cleaner. So what it does is it selects for this fundamental Gaussian beam profile. So this helps us to reduce our noise. And then it passes into this 3-optic cavity you see in this yellow-green color, which will recycle the light when it exits the beam splitter. But for now, it passes straight through to the beam splitter, and you're going to see it split off in 2 directions, just as we saw before in our really simple Michelson scheme. So now we're going to zoom way out, and you're going to see the power of the Fabry-Perot cavity. So this is a cavity that's formed by 2 parallel optics. So these are what forms the arms themselves. And they cycle the light up by a factor of about 300 in power. So it's actually about a megawatt that we have in each one of those arms at design sensitivity. So now we're going to zoom all the way down to the end of one of these arms so you can get a closer view of these mirrors. So they weigh about 90 pounds each. The beam radius is roughly about 10 centimeters. And if you squint, you can see that each one of these is held to the stage above it by these very, very thin fibers. And these help us to limit our thermal noise. But coming back to the light, so the light makes its journey through the arms. It travels back to the beam splitter. Half of it gets recycled in the power recycling cavity. Half of it travels down to this signal recycling cavity that serves a similar purpose. That's where it is now. And finally, it gets steered to this bow tie output mode cleaner. And so this will also clean the light by selecting for this fundamental Gaussian mode. So now we're going to see this space-time is very, well, exaggerated, highly exaggerated here, but in reality, very subtle stretching and squeezing of space-time. And as the light propagates through the interferometer, this is the pattern that you would see. and what we would call the output optics. And then this is the time series tracing out the very first detection. So this kind of gives you a better picture of a more realistically complicated detector. And there are over a dozen different subsystems that are all very tightly controlled with some really outstanding engineering. So I'll talk a little bit about each one of the foundational noise sources that give gravitational wave detectors their characteristic noise curve shape. So these come from an understanding of a Michelson detector. So particularly at higher frequencies, so like any other Michelson detector, we are dominated by this photon counting noise, this quantum shot noise that limits our ability to tell exactly when the time of arrival of a photon is. So this is what's governing this kind of rise in the noise over frequency above about a few hundred hertz. So that can be improved by more power. Essentially, just like any other counting experiment, your noise is going to go as 1 over the square root of the thing you're counting. So if you increase the number of photons that are circulating in your arm, your noise will go down. So we can do this a couple of different ways. So what's pictured there, just above the noise curve, that's the advanced LIGO laser. So we actually have really powerful lasers that at design sensitivity can get up to about 180 watts. And as we saw in our tour of the detector, we have these recycling cavities that will further cycle that power up to about 1 megawatt when it's in the arms at design sensitivity. And then in the middle frequency range, so this is our most sensitive frequency range. Currently, we're completely quantum limited, so we're still limited by shot noise here. But eventually, in the next observing run, we expect we're going to come to sit on this thermal noise. So what this is, you can think of it like a Brownian motion. So for example, you have particularly the atoms on the surface of each one of these optics, the coatings that are reflecting the light in the arms. So these will wiggle around quite a bit. And just again, to reinforce the sense of scale that the measurements we're making is on, that tiny little wiggles at the atomistic level are actually adding to our noise, or will be adding to our noise at the most sensitive frequency range. And then lastly, so this kind of dramatic sweep upwards in noise at lower frequencies. So this is dominated by seismic noise, by ground motion shaking, by ocean waves, by trains and people, and all manner of excitations of the ground. So the way that we mitigate this, so what you're seeing here, this tall structure in blue, so this is actually a fully controlled mechanical isolator, and there are several layers to it, but it works more or less the same way your noise canceling headphones do. So you measure the motion of the ground, you predict with your knowledge of your system what the resulting motion in your isolated system will be, and then you push on it a little bit to cancel it out. So you're actually always actively pushing on your equipment to keep it more still. So it's a pretty sophisticated piece of engineering happening there. So all in all, this gives us the noise curve that you see. So you might notice some kind of funny peaks here in frequency. So these are really strong sinusoidal features. So if you've learned about Fourier transforms, these are really high amplitude sinusoidal components. So we understand all of these strong features here. So you'll notice 60 hertz and its harmonics. That has to do with the US and Canadian power grid. And then at higher frequencies, you'll see 500 hertz and harmonics. And then this has to do with the mechanical resonances of these really, really tiny fibers that are holding the mirrors up. So what does this buy us? So all of this engineering and attention to noise. So this is to scale the sensitivity of our giant Michelson interferometer. So we're zooming in from a hydrogen atom all the way to the surface of the proton, and we're about to see to scale the relative displacement measurements that our giant Michelson interferometer can make. So it's 10,000 times smaller, and actually a factor of about two better than when this animation was made. So again, to give you the sense of scale. And I wanted to see if I can test your ability to spot noise here. So as you might expect for such an incredibly sensitive detector, we do have quite a few noise sources that do couple into our instrument's reading. So what you're seeing on the top, so this is the space-time strain data for LIGO Hanford, and there's some noise here that you can see happening. This is really well witnessed by a microphone. So this is the, just below it, so this is the microphone near our input optics, so near the pre-stabilized laser. So the y-axis is frequency, the x-axis is time in minutes. So I'll open the floor on the chat to see if anyone has any guesses about what this is. This is a new noise source as of the third observing run. This actually happened really pretty close to the intermediate mass black hole discovery that we just published. So if you'd like to see this feature in the data, you will be able to do that now if you go to our Open Science Center. Someone's been reading our A-logs. Not this time. Did not occur this time. It was a raven. But all pandemic. Yes, those are the days. So this is actually an Apache helicopter. So you can see these really nice harmonics, and you can actually see the Doppler shift as it flies overhead of the control room. Fire, oh no. We do have an excellent, well, excellent by some view, a striking, I'll say, picture of Rattlesnake Mountain, which is just behind the detector to the north, just completely on fire. I call it the Mordor picture, but not this time. This time it was a helicopter. And as you might imagine, sometimes these noise sources can pollute our data analysis. So particularly the shorter ones, like the Raven that was mentioned, is actually a lot more problematic for our astrophysical searches. So these can mask and mimic real gravitational wave signals and can affect our candidates. So this is a case study. So this is a retracted signal. So some of the astronomers here who follow up LIGO-Virgo events might remember this one. So this was from May of 2019. So it had a really promising, very low false alarm rate once in about 3 years. It had 100% probability listed of having a neutron star component and a remnant, so potentially some kind of a kilonova, and about 25% chance probability of being terrestrial. But what you might notice from the sky map, so it's actually about 20 gigaparsecs closer than 170817. And the sky map is really, really well localized. So this was actually retracted. So I'm going to show you a picture of the data, what this looked like at the time. So this is a spectrogram similar to the one you were just looking at, so frequency on the y-axis and time on the bottom. So this was actually an earthquake that happened pretty close to Hanford, which really reinforces a problem that the searches continually have, where you're trying to estimate the rate of chance, the likelihood of a chance coincidence of noise, and you don't really have the full spectrum of noise yet for an observing run. So this is the only nearby earthquake that we had, and it took some of our match filter searches by surprise. Me too, Daryl. Yes, me too. So this brings us to a project that I'm working on both within and without the collaboration. So this is the in collaboration portion. So thinking about the impact of different sources of noise on sky maps and our ability to resolve parameters of astrophysical sources accurately. So this is an example for another common type of noise that we have. So those arches that you see here, sometimes known as fringy the sea monster, so those are due to scattered light off of some moving surface, and you can actually trace the shape of the arches back to the frequency at which the surface is moving. But what you see as this injected simulated signal crosses this noise is the variance in the sky map. So we do start to get the estimates wrong. So the true injected value is that X that you see there. So this is one study that we have ongoing, and we actually have a collaboration with some astronomers here at McGill, and I think I saw Nick also on the line. Hello. So this is a project where we're taking information produced in these open public alerts, these LIGO-Virgo open public alerts. So purely public information accessible to everyone. So we're taking the coherence between the detectors that's encoded in the sky map and using machine learning to try to predict whether or not this is real. So this will be supplementary in addition to the information provided by LIGO-Virgo. So a postdoc here at UBC, Miriam Cabero, has just submitted this paper to astrophysical journals with a pretty good performance, particularly for having a pretty small training set of identified noise sources so far. All right, so summary of the O3 run. So we had about 70 total candidates, or sorry, about 80 total candidates. So 24 of them were retracted, so we had really quite high of a retraction rate. So some of that was dominated by these single detector candidates that were released by one of our match filter searches. But predominantly the most likely released source type at present for most of them is a binary black hole. There were 6 binary neutron star candidates, 5 neutron star black hole candidates, and here I'm just counting by what the most likely was that was released in open public alert data. 4 in the mass gap, so this is the lower mass gap between neutron stars and black holes. And then 3 most likely to be terrestrial, so glitches, and 1 burst event. So that's where we stand right now, having published 4 confident detections, and hopefully the catalog detailing the confident detections from the first half of the run will be coming out in the next month or so. And then just to really reinforce how these subtle changes in detector sensitivity can affect our event rates, here's a schematic, I suppose. So this is on the left, you're seeing either confirmed or candidate events from 01, 02, and 03, and the time of arrival that they registered in the detector. And then I just took out all of the commissioning time in between each one of these runs, and also the 1-month break in the middle of 03. So you can really see the rates dramatically increased on average in 03. We also had kind of a blip, an increased rate at the end of 02 that's still consistent with Pisonian statistics. But I want to draw your attention to these really subtle changes in the plot on the right. So this is the difference between each one of these observing runs for the LIGO Livingston detector in particular, where we've only changed for some fraction of our total frequency range by maybe a factor of 2 at most below 100 hertz. But it's as we're changing the sensitivity, we're extending our reach out into space, and then that actually gets cubed in terms of the total volume that we are sensitive to. So you get this really, really remarkable dramatic change in the average rate for a really subtle change in the noise performance. And again, we're going to improve this for the next observing run. So the LIGO and Virgo and KAGRA detectors are commissioning right now, with the hopes to be back up again at an even more sensitive range in the spring of 2022. All right, and I think I had hoped to leave some time for questions, so I think I will advertise that we were up to about a signal per week, a little bit better than that in 03 for the advanced LIGO detectors. So at design sensitivity, which is the target for the next observing run, we expect to be up to a confident gold-plated detection per day with a manner of other candidates. So here we're really going to be start to accrue these better statistics and this revealed population of stellar remnants. So I think I will end there, and I'm very happy to take any other questions.
Okay, thanks, Jess.
Thank you, Eve.
For everyone else. So we do have some questions on Slack, so I'll start from
Great.
there. So the first question is, can you explain a bit more about how you can use the anti-aligned spin to infer a hierarchical merger?
Ooh, that's a really good question. So essentially, there are different mechanisms by which we think that these binaries that we're detecting could form, and there are quite a lot of steps. So first, you need to form a black hole. That black hole needs to be, or a neutron star, I suppose, needs to be in a binary, and the hardest of all, that binary needs to merge, needs to be close enough together that through radiating away energy in the form of gravitational waves, it will merge within a Hubble time for us to see this signal that's, in the case of the latest event, traveled for billions of light years before it reached us. So what theorists, I should say, have hypothesized is that you might have a model where these two compact objects evolved together from the time they were stars. So they formed as a stellar binary, and then somehow, perhaps through common envelope evolution, they each undergo a supernova and form a really tight binary as two black holes, which could then merge within a Hubble time. So for that kind of a system, you would expect the spins to be aligned. You would expect them to be within the range of masses that you would expect. For example, not within the parent stability supernova mass gap. You would expect these to be below about 60 solar masses, and for them to have aligned spins. So a hierarchical merger, let's say that you had the system evolve and then it merged, and now you have a 80 solar mass black hole with a spin that's aligned with its orbital angular momentum. Let's say that this happens in a dynamically active environment, and through some mechanism, it captures another black hole and forms a really tight binary. But now you'd expect that binary to have this kind of isotropic distribution in spin. You wouldn't necessarily expect that population to have aligned spin. You'd expect it to be sort of random. And you'd also expect it to have a higher than usual total mass. So those are two of the expected signatures of this hierarchical model formation mechanism. Great question.
Okay, and the next question is, can you talk a bit more about how we can identify tidal deformalities of neutron stars just from the gravitational wave signals?
That's another great question. So the tides really come into play in the merger scenario. So I mentioned neutron stars in the context of continuous waves, where you have this kind of very sinusoidal type signal coming from some deformation in the crust of a neutron star that's spinning. That will also tell us about the neutron star equation of state, particularly at the crust. But yes, so tidal deformation will imprint a signature because we know space-time strain is related to the quadrupole moment, so the distribution of the matter. So as the stars are getting torn apart, as the tides are deforming them, that imprint will actually show up in our signal.
And I think you actually answered in part the next question, but I'll still ask in case you have more to add. So the next question was, how do gravitational wave signals help to constrain neutron star equation of state?
Oh, yes. Well, yes, I think we've covered the two main ways. So we haven't detected gravitational waves from continuous, we call them continuous sources, so spinning neutron stars yet, but we are getting to a really interesting range of parameter space where the detectors are now sensitive enough that we can start making interesting statements about the equation of state, just based on the fact that we haven't seen gravitational waves yet.
And I just got a note that there are some hands up, so I'll go there. So Bryce, could you unmute yourself and ask a question?
Yeah, sure. Thanks for the talk. It was really interesting. I have maybe one small confusion and a question. So if you could go back to slide, I think it was slide 18.
I think I'm going to have to flash. Sorry about that. Okay.
Yeah, so I think in your earlier like schematic of how we detect with this match filtering the masses and the distances to these sources, you mentioned that kind of by matching the amplitude of the signal, that's how you get like an inference of the distance. But when you have different amplitudes between Hanford and Livingston, for example, like what is the cause for this?
That's a fantastic question. And I don't think I actually showed a relative noise curve between Hanford and Livingston, but Livingston was significantly more sensitive. So this is not unexpected. So because the two detectors in the US are practically in the same plane, there are very few locations in the sky where if they had the same sensitivity, you'd expect the amplitude to be different. It's not impossible, but it would be very rare. But they did have pretty significantly different sensitivities in the last run.
Okay. And then my second question was, like, we had a seminar a couple of weeks ago, and there have been these independent groups who I guess have reanalyzed some of the LIGO data looking for these gravitational wave echoes. Have you guys, I mean, like the LIGO collaboration, discussed anything about this? I don't think there's any official statements about whether or not you see any residuals in the data from your end. Maybe just what are your thoughts on that hypothesis?
So there are some members of the LIGO collaboration and the Virgo collaboration who are interested in this, who do participate in probably some of the efforts that were referenced in this talk. So it's not part of our core science mission is probably the short answer to your question in terms of why there hasn't been a more official, broader statement, but certainly it's very interesting. And I think I know of a few different studies, maybe one off the cuff by Will Farr, who did a statistical analysis comparing essentially, within some time range after a signal, how likely it would be for something to have a signal to have essentially the same kind of a signature.
Okay, thank you.
It's of interest. Great question.
Yeah, it's very cool stuff.
Okay, Matt, could you unmute yourself and ask a question?
Yes. So thank you for the talk. It was really wonderful. I had one quick question about this before I asked another question just about this figure with the chirps. These chirps look a lot more symmetric than most chirps that I'm used to seeing. And I was just wondering if you could give kind of a qualitative or quantitative description on why that is.
Absolutely. So it's very well observed. We are not seeing a chirp here in the sense that what we'd expect is for the frequency to be evolving upwards in time. So that's more the in spiral phase, which because these are so massive, is actually happening out of the range of the advanced LIGO detectors. It's at lower frequency. So what we're seeing here is pretty much just the merger and the ring down, which is why it looks a lot more symmetric, and also why the burst search is much better able to resolve it. Okay, and then I guess I also had another question, thank you for that, about another previous talk we had where they were discussing the discrepancies in the noise profile, the shot noise modeling below a couple hundred hertz. And, they were using kind of, their theory behind this was that this could be used to restrict some models of quantum gravity. But I was wondering if you had any comments on that discrepancy. The mystery noise, yes.
The mystery noise, yes.
So I wish that I had thought to put a noise budget in, but essentially what we do when we're commissioning the detectors to try to understand where our different noise sources are coming from, we add up all the sources of noise that we can model really well. So shot noise is certainly very straightforward for us. It follows the power of the light in the arms like we discussed. But some of the more technical noise sources that are really tricky to model. So for example, when you're trying to control the power in each one of those optical cavities like we saw, so there's the power recycling cavity, the input mode cleaner, the signal recycling cavity, the two arms, we're up to 5, output mode cleaner, and also a whole bunch of other little optical odds and ends in the detector. All of those have to be kept on resonance completely independently for us to take data. And you can get these really subtle kinds of behaviors. So for example, if I'm constantly pushing on my mirror to keep the light resonant in any one of those cavities, and my beam spot wanders off of the center of the beam, and I'm trying to keep them both stable in length and also the relative orientation, and I'm pushing where I'm assuming the beam is in the center. Now all of a sudden I'm changing the relative length when I don't mean to. So this kind of angle to length coupling and some of these more subtle effects, that's what we think is responsible for most of that noise. And that seems to bear out in terms of, as we understand that noise better and better, we're better able to model it, and that discrepancy is getting steadily pushed down.
Okay, thank you.
Okay, I'm being mindful of the time, so unfortunately we don't have a faculty meeting with Jess because of our very strenuous teaching schedule. But we do have a student meeting, so I'll leave students to ask her questions then. Adrian, I know you had a question. Would you like to ask it right now, if it's quick?
Well, I mean, the question is quick. The thing is about the answer. I just was wondering, when you're getting one event per day, what's the collaboration's plan to prioritize what you're going to study in depth versus just put out there?
Oh, wow. That is a great question. And I don't think that we have an internal or external answer for that, but you're absolutely right that that's something that we're really going to need to do. So the model that we currently have, where we find these very incredibly exciting events that are novel in some way, and we produce a standalone paper for each one of these. So each one of the 4 results we've published so far, and then compile the rest into a catalog, that doesn't scale very well to an event per day, as you're pointing out.
Okay, so technically we do have like a 130-minute slot available tomorrow. If you have burning questions or like to talk more with Jess, just send me an email. Otherwise, let's thank Jess again for her amazing talk.
Yeah, thank you, everybody. This was a lot of fun.
Thank you.